So I know still a lot of you haven't turned it in yet. So just don't take pictures, okay? So I'm gonna show you the code here really quick. And since it's recorded, but I'm gonna trim these frames before I post it. Don't take pictures, okay? All right. This is one that we are testing for the moving objects, I think. So that's the main part of the code. And for the rest, I'm not really changing anything. If you look at all these ones are not being changed at all, right? Still the same. But for this part, I'm using a counter to control all these conditions. So the counter is counting up to 25,000, okay? And immediately I clear it. And under that control, I'm looking at if the red bar is at the very beginning on the left-hand side, or it's at the right-hand side, or it's in the middle. So these are three different conditions. If it's on the left-hand side, for example, the starting point, which is 35, I assigned 35, and you want to move it to the right, so which means you are adding 1 to the pixel, okay? To the left and right, both. So eventually it's moving to the right, okay? Because you are adding 1 to it. If it's already arrives at the right-hand side, which is 600 pixels, not exactly 640, but 600 is pretty much towards the end of the last pixel on the right. And then you want to move it back, okay? You want to move it back, so decrement by 1. Okay, so the rest of the conditions are just in the middle. So if it's in the middle, you have to discuss it. So it turns out to be either moving to the right or moving to the left, okay? If it's moving to the right, then the previous pixel number here will be smaller than the current pixel since it's moving to the right, okay? If it's moving to the left, then the previous pixel here will be larger than the current pixel here. So for the little red bar, I used a reference point on the left-hand side. So I'm looking at this point as a reference. So I'm comparing that to its previous value, right? So it's either, so it becomes like if, you can write a note if you haven't turned it in yet, okay? So for the if statement, these are the conditions I used. So if the previous one is larger than the current one, and also the left current value is not, so it's not at the end, either left or right, then you move to the left, okay? Because the previous value is larger than the current value, right? So you want to, wait. Previous value is larger than the current value, then it's moving to the left, okay? So you want to keep moving, -1, right? Otherwise, you want to use the else if, then you move it to the right. So basically, there are 3 different conditions, and this condition has another exception. That's it, okay? On the left, on the right, or in the middle. So in the middle, you have 2 different conditions. One is left, one is right. So moving to the different directions. And else, just add a 1 to the counter. So for the movement, definitely you don't want to move it at the speed of 100 megahertz, right? So that's why you are counting towards this value, and you can calculate. It turns out to be 0.01 second or 10 millisecond. If it's not reaching that point yet, just to keep counting. Keep counting. All right. Okay, so this is lab 6. For another one, I want to go through with you guys. Wait, we're at March 4th. This is going to be homework 6. Homework 6 will be this guy. I think this one is fine. I don't think you guys have a lot of issues on this. Module, top module. Yeah, this is fine. This one is fine. And another thing I want to talk about is a lab for this afternoon, for today's lab. Oh, no internet. We're almost there. Okay, Lab 7. So initialization has 3 different registers. It assigns these values in a certain sequence. You can definitely swap them. It doesn't really matter because they are being identified by some of the signature bits in these bytes. Okay. So I think there's just only one thing I want to clarify. So this is a new figure I added to the tutorial just over the weekend. I think it's just necessary. So the code are provided in the textbook. So there's a PDF I posted over here, I think on the top of the page. If you scroll to the top, so these ones, they have the original code in there posted. However, you have to make some modifications. And one of the modifications is the ports. Okay, so if you look at the peripherals of the LCD, this guy is the LCD driver. So this is going to be the chip being implemented to the IPGA chip. And eventually, I was interfaced with all the hardware on the IPGA board, and this hardware is being connected to some of the pins of the LCD module. If you look at LCD's pin out here, so there's a RS, there's a VCC and ground and contrast and RW enable, okay, and the rest of them are just the digital pins, the data pins. So the data pins are easy to connect. So if you look at the module, the system diagram over here, the digital pins are shorted to JA pins. And if you look at your constraint file, so the JA pins are being commented out. You need to uncomment them before you synthesize your code. Okay, keep in mind. Get into a constraint file, find out the JA pin, JA ports. And these are just the general purpose IOs. Instead of all the other IOs are already shorted to some of the peripherals, including the LCDs and LEDs and 7-segment displays. So these ones are made available for the customer. So these are not shorted to anything else. These are just the GPIOs. So JA, JB goes to the constraint file, uncomment all of them. And for the hardware, directly short. So this reminds me about that. So I have to give you a lot of jumping wires and those all these 5 volts power supplies as well, the power supply modules. So use the jumping wires and plug into the ports of the JA ports and connect to the LCD's D0 to D7 accordingly. Again, the EN, the enable pin, connect to JB0, and RS connect to JB2. If you look at the Verilog code provided by the textbook, there will be a register code WR_EN. It's a write enable, and that's not a port. Keep in mind, it's just a register. It's an internal register. You can give a 1, give a 0, doesn't matter. So it's just receiving a 1 to enable the writing to the digital pins. Doesn't matter. It's just a register. You don't need to connect this to anything else. It's just a register type variable. Okay. I must be thinking, so the LCD driver is outputting data values from 0 to 7, 8-bit, right? So that's the output. But for the module, for the digital module, where is the input? We always think about input and output, right? So this guy is outputting values to your LCD through the IPGA. So the digital system must have input. So what is the input? Where is the input?
There's like a bunch of input pins inside that PHW board. So like.
I mean the data. The data. There isn't a microcontroller communicate with it, right? So that all the inputs are from the internal you write it into the IPGA. So these are just the ASCII code, like bytes. You assign them to regs, to the register data type variables. So you can see in here, the character, all these bytes are being put into the register. You actually write it into your Verilog, and eventually they will be interfaced with your LCD driver and send the characters or bytes to the LCD driver, and eventually arrive at the JA ports, which is shorted to the LCD's data pins. So the switch can be used. So the switches are not real data. So I'm not asking you guys to use this 8 switches to encode that ASCII code, right? We're not doing that. So the switches are just a switching in between the characters. So for example, if switch 0 is on, I'm sending this character to the output. If switch 1 is on, I'm sending another character to the ports. Okay, and clock is always being used. It's a 100 megahertz clock. It's updating all the data, all the digital systems, all the ports, and just update everything in the system. And you can see that from the in-class exercise we went through last time, you guys all know that RS, when RS is 0, it's selecting the IR, which is the instruction register, because they are using the 0 to 7 data pins. If you look at this one is being multiplexed, so it's being whenever you are sending a data in here, you have to tell the LCD module if you are sending the instruction or data, right? And which is controlling that? RS. So keep in mind, this is super basic for the LCD. This will be on the final exam eventually. Okay, so RS is controlling that, right? So if RS, this pin is 0, the data appears at the D0 to D7 is actually the instruction. Otherwise, it's going to be real data. Okay, so the instruction could be all these, like these ones are instructions, right? So these are setting up the mode, setting up the certain modes for the LCD to display. It could be the blinking the cursor. It could be like 1-liner, 2 lines, and all these kind of things. We don't have to worry about too much about it. You can play with it if you want, but we're just using this default setup. And so if you look at the code, here's only one thing I need you guys to understand. Okay, you scroll to this main code here. I post it as a picture on the website. So you can see that RS was assigned. So 1 was assigned to RS at the very beginning. All right. Oh, sorry. You can see here. RS is so 1 is assigned to RS at the very beginning. So you can see this is the main block of the code, and always at the clock, it's gonna update everything. Keep in mind, everything's getting updated. But however, originally it gives 1 to RS. However, when I want to start using LCD, I want to set up all the modes first, right? So I do need a 0. I need a 0. So you can see this is just an initial state. So which means if I'm not really doing the init state, by default, I'm actually sending code, sending data to it. You don't have to worry about that, because if eventually, whenever the clock updates everything, the state, the very first state will be init, will be the initial state. So the first time it runs, when we part it up, it gets into here first, init first. As you can see, RS is 0, which makes sense. We need a 0 to set up all the modes. Okay? And you can see the init has 4 different bytes, and you can see it's gonna start going through all the index in here. So the init, you can init count here. These are all the init bytes, the settings of the bytes. Okay, so these will be given to the data port here to data out one by one. So you can see it's gonna start counting, and it's counting to a count max. You know, it's the parameter's name is clock underscore parameter. And I'm gonna ask you how long it takes to count to this number later, but during based on the calculation, it's just about like 1 millisecond. It's about 1 millisecond. If you look at the timing diagram over here, all these minimum time is several hundred nanoseconds. Okay, so the code, the example code provided by the book is not really considering the time. So minimum is a few hundred nanoseconds, right? It's always delaying like just 1 millisecond. So always like way longer than the minimum. So there won't be any issues with the timing. But if you want to run it faster, you probably want to reach that minimum time limit. But now we're just doing whatever, just 1 millisecond. Give it enough time to do the time delay and all these kind of things or set up. Okay. So do a 1 millisecond time delay and eventually give a 0 to it. So you can start. Oh, 0 means it's enable writing. RS is you start writing instructions, but enable is really writing. This is another important stuff. Okay, not too many, probably just 2 or 3 important points over here. Okay, so the first one is you need a 0 to give to select IR, and second one is you need to pull enable pin down to 0. I know this is really dry, you know, but not too many important points. This is the second one. So enable pin has to be pulled down to 0 to write whatever add data out. Okay, write it to the D0 to D7 pins of the LCD. That's where that writing the data happens. Okay, you pull it down to ground, then it happens. Otherwise, it won't happen. If you look at the my timing diagram over here, you can see. So you have to pull this down first, pull RS down first. So you are trying to write instruction byte, okay? And then you pull this down. So I'm having 1 millisecond time delay. It requires a few hundred nanoseconds. 1 millisecond is enough, good enough. And then I'm gonna pull down enable pin as well. So whatever at the data out pin, the D0 to D7 will be written to that LCD D0 to D7 module. And we're not reading from it, keep in mind. We're not reading from it. Since we just want to send something to the LCD and display. So this is pretty much the only thing you need to know. Almost. Okay? So later on, you want to write data to it instead of instructions, but data are also bytes. Like the instruction bytes are also bytes. You have to pull this up, have to pull RS up to 1. If you pull it up to 1, there will be a few hundred nanosecond delay required, and then you have to pull this down again, enable down again. So to enable that write event as well. So in that case, there will be a few hundred nanosecond time delay required. Always, we just use 1 millisecond, which is fine. So we don't worry about the time really much. Okay. But in the future, if you need to, if the time is very sensitive or becomes significant, then probably we want to care about the time delay here. But now we don't. Okay. Okay. So these two important parts: 1, 0 or 1, picking up IRDR, and pull down EN enable pin to write it. Okay, and then once this is done, the state moves to wait. Okay, moves to wait. So which means all the instructions are written. All the instructions are written, and then it moves to wait. So if you look at the wait state, could you tell me if RS is 1 or 0? What is the RS over here?
That's 0.
Did I define? That's the third important point here. After this, we're done. Okay? I'm not teaching the nitty-gritties of the code. It doesn't make sense. It's making people sleepy. I'm just telling you the important ones. 3 different points. 3 super important points. Okay? First, told you. Second, here. Third, where's RS for the wait state? What is the wait state doing here? So the wait directly jumps to write, so they are linked. And in the write, seems like you are writing data in to data out. So data in is going to be the ASCII code. All the characters are going to display on the LCD. Okay? So basically you are writing data to it. So if you are writing data to it, RS need to be what? 1. Did I set it to 1? Take a look. Did I? Where? You don't see it, right?
Yeah.
What about here? Set to 0. What's happening? How that works? Keep in mind, super important concept right here, okay? How that works? How RS becomes 1 for the wait and write state?
Well,
So, like I told you guys, Verilog is a hardware description language. It doesn't like C++ or Python, right? So it's running as instructions, so the instruction pointer taking one by one and executing in the CPU, right, as a loop and coming back and forth. So this is like an implementation. After everything is implemented, it's like a hardware. It's ready like a chip on the FPGA. And the clock signal for the always block over here is updating all the states of the registers. It's basically on the left-hand side. Everything on the left-hand side will be updated every time the clock arrives. So every time clock arrives, it's like remember the D flip-flops we introduced in VLSI and also probably in logic if you are not in VLSI. When clock arrives, all the value from sitting at D will be sent to Q, right? So all these things are being updated. The same concept. Everything from top to bottom, everything will be updated.
yeah.
So if you set RS to 1 at the very beginning, okay, still during the same clock cycle, okay, so when clock arrives, doesn't matter, the positive edge, negative edge, doesn't matter. So when the clock arrives, okay, during this same cycle, RS becomes 1, this becomes enable, and so it's checking all the if statements, okay, so it's moved to this state, init state, and then RS immediately being set to 0. Okay, so this is being set to 0 immediately, and then you are able to do all these kind of things. Okay, and then after that clock cycle, after this is getting set to 0, after the init state, you can see I immediately change the state to wait. Okay, and then it comes to wait and when to write. So whenever the next cycle of the clock arrives, this is still being executed. However, the init state won't be executed because it's not at the state anymore. You know what I mean? The case is going to skip. So the case statement is going to skip that init state and directly get into the wait and write state, which you don't have to set your RS anymore because it's already set at the top. Okay, so it's all controlled by the state. So you can see how powerful the state is. So by using or you can say it's a finite state machine, eventually you are able to have more freedom to control all these, your code or design by using different states.
Actually, the state only execute once?
The state is just a state, it's just a byte. There's, what do you mean by execute once?
Like, it will happen once and then at every clock cycle it won't matter anymore because we already did the case state.
No, every time it comes to the case state and trying to see what the current state is, right? And then directly jump to that state.
What is state?
What is state? State is just a byte, just a variable. Let's see what the state is being defined as over here from the from the code in the textbook. Oh, depending on how many states do you have, it could be a buy if you have a 250 states, 256 states. However, we only have how many? Init, wait, and write, 3, right? So for 3 states, you need 2 bits actually will be enough. However, I put a 3 bits over here, just overkill. I think 2 bits will be enough. So 2 bits will give you 4 different states. Just a register type. You can see it's just a reg, right? Just register. It's like a flag, okay? We are coding with C, with microcontrollers, it's like a flag. All right. Only 3 important points over here, okay? But all the rest are pretty simple, either incrementing, decrementing the counter, assigning 0, setting up or reset everything, and jumping between all those different states and doing the display. So it's pretty straightforward. And don't forget to do all the connections, uncomment all the constraint files, the JA, JB ports, and the labs are pretty simple. It doesn't like the previous labs. It's getting more and more difficult from task 1 to task 3. So this is pretty much just repeating. Okay, task 1, task 2, task 3 are very similar, only changing the very basic characters to be displayed on the module. I think the format and all these kind of things. So I think this is relatively easier compared to the previous ones. All right. The last thing I want to talk about is the software. So if you look at the schedule for the labs for this class, so we are at here right now, and next week will be the Picoblaze, the software lab. So after the tutorial covers very basic assembly coding, and for the lab it's a little bit more complicated. So it takes 2 weeks. So eventually you can see we are pretty much spending about 3 weeks on the software. And moving forward, I deleted one of the regular tutorials on USB and I moved it to the lab because I don't think we have enough time to cover all these topics in the class. So Lab 9 will be the USB interface, doing all the parity check and all these kind of things. You guys are going to use a keyboard to interface with your IPGA. And after that, we'll do some course project. Okay, so the course project is supported by a funding, supported by the college. And to make it meaningful for this class, I'm thinking about any community problems that can be solved by either embedded systems like IPGAs or microcontrollers. But the microcontroller has to be IPGA based because this is not a microcontroller class. It could be any problems. Think about, I can probably give you some topics later. I have to think about it when I'm running on the treadmill in the morning. That's where I got creative every day. And for example, okay, so back in home, we need a power, okay, I want to use solar panels, and the solar panel control board probably need an IPGA to do something to make it more efficient. Or anything, okay? You want to say, I want to change our traffic light to the one I designed on my IPGA. Doesn't seem to be fun, but anything have a broader impact you can think of. Can be water treatment, can be, some of you are in junior design, you are in junior design for the LED stuff, killing bacteria, right? Anything an IPGA can control, can contribute to it. I mean, anything. And do some research. Okay, eventually it's going to be a report, right? Report needs some literature study, introduction, research, instead of just following tutorials. So you want to see what this technology can do to make the world a better place to live. Okay. The topic too big, right? So the IPGA is not smart enough to make the world a better place to live. I think the Picoblaze can do a lot of more things as a microcontroller. So eventually we are introducing SPI. So if you look at the SPI here, probably you have used a lot of sensors, digital sensors that has a SPI port with it. Okay, so all these input and output clock and enable pins. You can search for any sensors that has a SPI communication port over there and interface with your IPGA and do some meaningful applications. It could be something similar to what you have done in the past, like a CO2 sensors or air quality detections. But let's use IPGA to do it. Okay, and you can see you can hard code a SPI block in your IPGA and directly interface with a commercial SPI, which is amazing. Like what you did with the VGA, right? So the IPGA had nothing in it. You program the protocol with the VGA, and you eventually can display something to the monitor, which is amazing. And you are able to code up something to talk with the hardware, which you cannot see inside the box, similar to the SPI. Okay, so you can another very popular application for SPI is SD cards. So you can, I have a lot of SD cards adapter in my lab. You can find out the SD card adapter, plug in SD card is usually SPI, right? SPI, and just write all the protocol, and eventually communicate with the SPI, the SD card, to write and read data in and out for the SD card. It's another really fun project. So it could be a sensor from the light, from anything, from a sound, and eventually being digitized and being stored in the SD card. Okay. So this is a SPI communication protocol, and here's a regular SPI sensor. It's a light sensor sending light intensity in the form of bytes to the IPGA board. Okay.
Actually, is the group project individual? Is the project individual or is it group?
We can make a group, probably 2 people on the team. Okay. Depending on you, it's not required. If you want to just work on it by yourself, which is also fine with me. Okay. So now let's take a look at this one, the last one I'm going to talk about today. One thing I want to clarify, since last time in the in-class exercise where they went through the registers, remember the test, compare, keep in mind some of them will be on the quiz, okay? So I'm asking you, after this instruction, what C would be, what Z would be, all right? Things like that. And for input, I just added 2 more snapshots to the tutorial. You can see, because I don't think the previous the one I posted on the top has that detailed information about it. So for the ports, it could be a little bit confusing. We're talking about the ports. So the ports are being used whenever you use the input and output instruction. Okay, just look at this one. Input or output instruction. So during these instructions, you are able to receive data from the input ports or send data to the output ports. And so you can see the input instruction, you can directly receive, you can use the address of the port in the register, or you can use the address of the port as a immediate value here, or byte over here. Either way, it could be this or it could be this. So my question for you guys is, given that the Picoblaze core has 256 ports, so where are these ports? And each port is 8 bit. like 8 bits, right? And there are 256. So which means you need 8 bits of address to resolve all these different entries, right? So it's eventually 2 to the 8th entries or address to access all these 256 entries of the ports. Where are they?
In the gate array?
In where?
Maybe in the gate array? I don't know where else would it store that many.
Are these physical pins of the IPGA?
No.
Soft core, right? Soft core, right? Before you, I mean, the IPGA comes before the soft core, so there isn't any physical. It's impossible, like 256 by 8 pins. It's gonna be a huge array of pins, right? It's impossible. But that little chip, 8 Arctic 7, is tiny, right? It's impossible. Then what are they? Where are they?
Well, they're digital, aren't they?
If you look at this, okay, let's look at this diagram. Okay? This is the last thing I'm going to talk about today, okay? I won't bore you further. This is the last one. I know, you know. Look at this. So the port ID has 8 bits. So the port ID is what? The port ID is address. That's one thing you need to know. Can be on the quiz in the future. The port ID is the address. And this one only shows you two different selection bits, like the address for this guy. So it's providing like 1000100111. So there will be 4 selections, 4 different choices, like a mux, right? So eventually you can choose 1 from the 4. So you only need 2 selection bits as a mux. However, you can see port ID has 8 bits, so eventually it just doesn't have the space to draw all of them, right? So eventually there will be 8 lines to add for the address, and there will be a mux to select 1 from how many?
8 bits? Yeah.
8 bits,
Yeah.
and you can have how many combinations from 8 bits of address?
2 to 8.
To the 8 is what?
2.
256.
Yeah.
So for 256 mux, it's basically like 1 versus 256 mux. Okay, so the next homework assignment is to design the mux. And due date is 2030. Anyway. So there will be 256 entries, and it's selecting 1 of them and picking it up and send it to the import. So the import is the core. That's the CPU, okay? And the CPU has 8 bits to receive the 8-bit data from one of the ports. So my question is, why did the designer design 256 ports? And definitely the modern CPUs probably has a lot more, like 2 to the 64s or something. I don't know. However, why is this beneficial? Like for the microcontrollers, you need more pins sometimes. If you buy a higher end microcontrollers, for example, the Arduino Uno compared to the Arduino Mega, right? The Mega is like $4 for each, and Uno is 75 cents or something. I don't know. And no, it wouldn't be 75 cents. $1 probably. And $1 microcontroller. So the Mega chip probably has how many? Maybe like 32 or something pins. And this Arduino Uno is the 28 pin microcontroller. So eventually, if you run out of pins, you want to switch to Mega. That's what we usually do. Okay, switch to Mega. So, however, these 256 pins are not being added to the pins, the physical pins of the chip. Eventually, they are not available. They are inside. Okay, so if this core has a CPU, has an ALU, has the ports, has the peripherals, a data path, all the control units, and all these ones are getting synthesized, and eventually the Verilog is being converted to a huge digital block, and that digital block has these 8 bits and 256 of the 8 bits ports inside the block, okay? And these are not physically shorted to the pins. But why these are still useful?
That's because you can have multiple microcontrollers on the same FPGA, right? So you can have them.
Yeah, that could be one of the applications, right? Also, you can, for example, you have other peripherals like ADCs, right? It could be the so like your Arduino Uno SoC chip, okay? So that's the Arduino Uno has a CPU, and also it has SPI, right? Has I2C, has UART, all these communication ports, and it has what else? ADC, I already talked about ADC, and a lot of other things. So all these ones are digital blocks being put into the chip or the microcontroller, and these ones will output data. And sometimes when you are coding one system, one application, and these ones are working at the same time, so they want access to these ports at the same time. So you can eventually connect to a lot of different peripherals inside the chip. Okay, so you can add a lot of new things to it and connect them to the ports. Okay, so whenever you use a port ID like an address, so I want to pick up, for example, port 10, and port 10 will be, the ADC's output, and eventually the ADC's output will be sent, the byte, that one byte as the output will be sent to the CPU through the port. So it doesn't like the physical pins of the chip, right? You don't have that many pins for the package, but however, for internal pins, you can add as many as you want. So by looking at this example, you can feel that some of the advantage of using IPGA over microcontrollers. So microcontrollers are basically just the C program instructions, right? So it has to be the instruction pointer taking out everyone each time, and you have no freedom or options to modify the hardware. Okay, so it has a lot of limits. When you are running something at a certain speed, you have to worry about the speed here, the speed there, and the clock cycles and all these kind of things. But for ASIC, it's application-specific ICs, and you can do with IPGAs. You have all these ports available. Okay, if you want to make this not a general-purpose microcontroller, but an ASIC, you can directly just use this as an ADC. Put an ADC over here and directly communicate with your CPU, and you can modify the clock cycles and make it just for that ADC. Make it as fast as you can, without worrying about anything else. So it doesn't have to be compatible with anything else on the general purpose microcontroller. Only has to serve your certain application, the purpose. So IPGA sometimes can be way faster than microcontrollers, and that is one of the reasons. Okay, so you can customize every single thing for the system. Okay, so when you are programming that, we are trying to access these ports for the input and output. I didn't break my promise. It's still the same topic. Okay, it's the last one. Just a little bit long compared to the first one. All right, so look at the instructions, assembly code, then we are done. Okay. Here. There are so many different ports, and you can use any one you want. I used 00. There are 256, so it's up to FF. Okay, so it's basically from 00 to FF. Okay, so the only thing you want to specify is, okay, so this one need to be shorted to the switch. So you put it into the top. You'll see the example code provided in the tutorial. So basically, I connect SW to input. So eventually, the switch is being shorted to all the input ports. Anyway, we're not using any other ports, so it's fine. So eventually, whatever switch you put a different value combination to the switches, it will be sent to this port, and eventually S0 will receive it. That's a register inside the Picoblaze core. Okay, so I was trying to see the more details about the hardware connections, but I can't. It's not being released or disclosed. So I just do whatever we can. Okay, I found another document for the hardware. I'm going to show you really quick after looking at this assembly. Okay, so for the output, it's the same thing. So the input ports and output ports, even though they have the same port ID, but they are different ports. Keep in mind. So the input switches value goes through the 00 ports and arrives at S0 register in the CPU in the Picoblaze microcontroller. And then you can assign the value in S0 to S1 and load it to S1, and then you add something to S1 and then pass the S1's value to output port 00. Keep in mind, it's a different port. It's output port, but the address for that output port is 00. So there is another 256 output ports with the microcontroller as well. So this is being sent to the output ports, and eventually you connect these output ports to the LEDs for this application in your Verilog, and all these code are provided. Okay, so the first example you go through it. It will help you understand what's really going on here. And so for that document, another reference I was talking about, which is this one. So this snapshot is from the official KCPSM6, this course official guide. You can see this is the one I showed you guys last time. Remember this one? These are the slides. However, I found another one which is really good as well, which is this guy. It's right to post it. It's UG129. It's published online. It's called Picoblaze 8-bit embedded microcontroller user guide. Okay, it has more details about block diagrams of circuits. Okay, it's pretty long, but it has a lot of really good details about the instruction sets and the block diagrams of circuits. So I think these two will be the main references for this lab and tutorial. To keep my promise, so I'm done with the lecture, and let's break for 5 minutes. Then we'll do the quiz.
Sounds good.
Okay.